Hey everybody. I'm starting off with a bunch of stuff on the screen this time. Um, Watch this when you have time to think and your brain is a little fresh. Okay. I am going to go off. Uh, let's just get started. Chapter 7.4 is something called annuities, and an annuity is a bank term. Uh, we don't use it particularly too often now because the idea of an annuity, we just call it an investment nowadays. Okay. But for what it's worth, what an annuity is basically a geometric series in an investment context. Okay. To remind you, to jog your memory of what a geometric series is, I mean, you've probably just did the problem set so you would know, but geometric series is the total sum of a certain number that's constantly increased or decreased based on a certain common ratio. So whatever the first term is, you multiply that by the common ratio to the power of how many terms they are, minus 1, all divided by the common ratio minus 1. Okay, and we prove that this formula was true. Now imagine this idea in a investment context. So instead of total sum, that would be future value of your investment, your final investment. Does that make sense? I hope so. The first term would essentially be the amount of money that you invested at the very beginning. R would be all of this, right? That would be like, let's pretend R was like 12% and you did it monthly. That would be 1.01. That would be the amount, the number that you're constantly multiplying the initial value by. So that is your common ratio. So it's color coordinated. N, in other words, this time it's N times T. The number of terms for the geometric series would be the number of times I compound per year multiplied by the number of years in an investment context. Okay, so it plays out. You're going to have to bear with me in the explanation of why this makes sense and so what you need to watch out for when you're plugging this in. If you're not interested, low-key shame on you, but at the same time, if you just want to see how the formula is used in the examples from the textbook, use the timestamp, okay? So I'm going to, as part of the explanation, if you're still with me, I'm going to propose a fictitious situation that you might find yourself, relating to in the future. Let's pretend you get yourself, you go to university, you get yourself a part-time job, or whatever, and every month I ask you as your grade 11 teacher, how much money are you willing to, do you think you won't miss? How much money can you save a month and you won't miss it? Like you won't see it even gone because you just sort of leave it there, right? Let's say you make 500 bucks a month and you buy yourself a game a month, you buy lunch once in a while, you buy dinner a couple of times, go to the movies. How much money will you have saved and you're not going to miss? Can we say maybe 100 bucks? Let's say you're able to save $100 every month, okay? And how many years are you willing to do this every single month? Well, because it's month, by the way. That's 12 then. Let's pretend you're going to do this during your university career. So the amount of time that you have is 4 years. Every month during the 4 years, you're going to save $100. Do the math. If it's $100 a month times 48 months during your high school or as a university career, you should have $4,800 left in the bank. Cha-ching! That's a amazing, end of university vacation reward for yourself. You go to Europe and blow all that. You can go to Mexico for Cancun, whatever, and have enough money to do whatever you want and then some, whatever the case may be. But this is today. This is 48 months from now. And let's pretend at the end of the month, you are going to be able to put in $100 because you have to work, right? So today you have nothing. But at the end of the first month, you will have put in $100. At the end of the second month, you would have put in $100. At the end of the third month, you'd have to put in $100, $100, $100. So at the 48th month, you would be able to save $100. At the 47th month, you put in $100. 46th month, you put in $100. 45th month, $100. 44th, $100. And 43rd, $100. And a whole bunch of $100 along the way. Okay, saving up to $4,800. Good for you. But here's the thing. Let's pretend because you're doing it for 4 months, the bank is like, oh, look at this guy. All right, it's only 4 months. We can't do much with the $100 a month. So how about we give you a rate of 1.2% a year? I say this because it makes it easy for me to calculate. If I'm doing a 1.2% a year, how much am I able to actually gain interest per month? R divided by N, so that's 0.012 divided by 12. I am gaining 0.1% every month. I know it's not much, but it helps me with calculations. So if that's the case, let's do the calculations. On the 48th month, did we have just graduated university? Did this $100 gain any interest? The answer is no. But let's look at the next month. This $100 was saved 1 month before we graduated. So by the time we get to the 48th month, how much interest did I gain? Well, it would be, do you remember compound interest? The final amount is equal to principal 1 plus R over N to the power of NT. Well, the final amount is going to be $100 multiplied by, remember, 1.2% divided by 12. It's going to be an addition of 0.001. And how many times did we do this? Well, we only gained interest for 1 month, so this only happened once. This would be 100 times 1.001 to the power of 1. Okay? So if that's the case, the $100 that I saved 2 months ago, how many months did I gain interest? Well, it would be $100, 1 plus 0.001, 2 times. Right? The $100 that I saved 3 months ago, how many months did I gain interest? It would be 1.001 to the power of 3. And 4 months ago, how much interest did I gain? $100, 1.001 to the power of 4. And this one, 100 to the power of 5, right? And if I keep going, take a look at this one. How many months did I gain interest for the very first $100 that I put in? Well, how many months passed between 1 and 48? 47. Doesn't that look familiar? That is basically 48 minus 1. That is n minus 1 in a geometric sequence. Except I need to correct myself. It's not a geometric sequence. Am I looking at one number? No, I'm looking at this $100 plus this much plus all that plus all that plus all that plus. Because all of this is still in my bank account. It's constantly gaining money. So this is not a geometric sequence. It's a geometric series. What is the first number? What is the common starting term 1? What is term 1 of this geometric series? Term 1 is 100. That coincides with how much I put in every single compound period. Okay? It corresponds with big R, repeating payment. Okay? What is My interest rate. What is r to the power of n? Well, in this case, the r, the common ratio happens to be 1 plus 0.001. It happens to be 1.001. That's what I'm constantly multiplying by in the geometric series, which is 1 plus 0.001, which is 1 plus 0.012, the annual interest rate divided by 12. And that is 1 plus r over n. Right? It's all coming together. What is the number of terms that I'm adding here? Well, that is going to be, I have, starting with 100, which is 1.001 to the power of 0, I have 47. How many numbers are actually here? It's 48. So the number of terms, little n, coincides with, so little n in the geometric series is 48. In the financial investment context, the number of compound periods times the number of years is 12 times 4, which is 48. So they match up. Every single one of these numbers match up. And under the common ratio -1, that's 1.001 minus, it all matches up. Okay, so let's clear this. Again, I may not be doing it justice, and I wish I could explain it to you or give you an opportunity to ask specific questions, but I'm going to clear the screen and specifically address the formula itself. Clearing in 3, 2, 1. The future value of your investment, okay, the total, is going to be how much you are able to repeatedly put into your savings, capital R. And that is going to be 1 plus, multiplied by 1 plus r over n, all to the power of n times t, minus a big one. And this is going to be 1 plus r over n minus 1. Now, notice how the plus 1 and the minus 1, they're going to subtract with each other. So depending on the textbook, you may also see just r over n as the formula. The textbook also seems to not like to write r over n anymore because, whoa, we're now getting into finances. There's no r over n. They replace it with the letter I for the interest every time we calculate. But that's not necessary. As long as you know how to identify r and n, you're going to be doing that anyways. All right, so let's try seeing this formula in action in some of the examples from the textbook. Example 1 from page 446, that says, at the end of every month, Oshi deposits $100, in an account that pays 6% per year, compounded monthly. He does this for 3 years. Draw a timeline, no thank you. Determine the amount in the account after 3 years, I can do that. How much interest will the annuity have earned? Oh, I totally forgot to actually calculate the previous example, didn't I? I'm gonna do that. Going back to the video, shoot, I meant to do it just to surprise you of how an annuity can help. Before, we know that we saved our own cash of $4,800, but if I were to do the future value of $100 every single month, 1 plus 0.001 to the power of 48 minus 1, all divided by 0.001, I would get 4,914. You know, that's still not too bad considering you're only getting 1.2% a year, okay? Let's see what happens if you're getting 6%, which is a little bit more reasonable if this was invested in some kind of, let's say, ETF or mutual fund, whatever. All right, here we go. The recurring payment in this case is going to be $100. The rate is 6% per year. The compounding is monthly. The amount of time is 3. How much will he have? So what's the future value going to be? Let's do it. $100 multiplied by 1 plus 0.06 divided by 12, all to the power of 3 times 12 minus 1 divided by 0.06 divided by 12. 0.06 divided by 12 plus 1 to the power of 36 minus 1 times 100 divided by you should have gotten $3,933.61. Comparing that, remember, he deposited $100 every month for 3 years. That should have resulted in $3,600. So the actual interest would be the total amount minus the cash that we normally have. $333.61. In 3 years, he earned $333.61. Not bad. Okay, clearing again, we're going to go into example 2. Example 2 from page 447. It says, Sadia needs $4,000 for university tuition when she graduates in 2 years. She plans to make deposits into an account that earns 6.5% per year, compounded bi-weekly. Draw a timeline. How much should she deposit bi-weekly? I'm not going to draw a timeline because I did that for you before. Let's try it. I need 4,000. In other words, my future value at the end of my investment is 4,000. It is not my recurring, nor is it some kind of present value. There's nothing like that here. Okay? Ooh, geez, what have I done? Anyways, okay, future value is 4,000. The amount of time I have is 2 years. It's going to be compounded bi-weekly. How many weeks in a year? 52, half that. That's going to be 26 times a year. The rate is 6.5% a year. Let's do it. What is my recurring payment going to be? 4,000 is equal to my bi-weekly payment, 1 plus R divided by N to the power of 26 times 2 minus 1, all over 0.065 over 26. So I'm going to do the bracket portion and divide it with the interest rate. 0.065, 26 plus 1 to the power of 52, subtracted by 1, divided by this. Okay, that means my R is multiplied by, that means my R is going to be, divide both sides by that decimal. I got 72. Every 2 weeks, Sadia is going to deposit $72. In 2 years, she'll have $4,000. It's not a bad deal. Okay. Example 3 asks you to use a, I guess, a calculator aid to figure out what the mystery interest rate is. Yeah, there actually is no way to calculate what the interest rate might be at this time because you don't have the higher math rate or the logarithms and whatnot. Not, wait, does logarithms help? Yes, it sort of would, I think. Okay, so instead of giving you more examples from the textbook, I'm actually going to ask you a personal question myself. Okay, and this is going to be very important, and this is what gets me really excited. Ask yourself this, all right? How much do you want when you retire? Be honest. Go think about what kind of house you want to live, whether you want to afford a fancy car, whether you want to go travel once a year, whether you want to have fancy restaurants and go out with, your significant other or whatever in the future. And calculate how much you would need to live that kind of lifestyle from the age of 65 until you pass away. Right? Just do the calculations. I'm just going to go off on a limb and say, I want $2 million. Okay. If I have $2 million at the age of 65 years, I could spend a little bit of money, okay, every single year. And then, the amount of money will continue to grow for me, whatever. And I will live a lavish lifestyle and I'll die happy. Okay. Well, tell me then, if your time is going to be 65, I'd like you to pretend you're going to start investing as soon as you turn 18. How many years are you going to invest? That's going to be 47 years, okay? And typically, if you do an investment or you do something, your bank is going to give you your interest every month. The question is, how much interest? Well, let's pretend that you find yourself a decent investment. Right now the stock market and ETFs and stuff isn't doing too well. S&P and whatnot, it's very, very volatile because of the coronavirus. Let's pretend on a good average rate, you're going to get yourself 5% every single year. I think that's fair. Okay, it's not too low, it's not too high, considering it's 47 years. All right. What is the amount that you need to put in every single month? That's the mystery. All right. And you will be very surprised. Do you think that a retirement with $2 million as a nest egg is too much? Well, let's do the calculations. Math, from all the practice you've done, you know this formula works and it doesn't lie. Math don't lie, okay? So if your future value is $2 million, your recurring payment is a mystery, but you know that you're going to get 5% from the markets once every month. So that would be 12, and you're going to do this for 47 years. Every single month for 47 years. Do it. What is that R going to multiply? So it's 0.05. Divide that by 12. I'm going to add that with a 1. That is to the power of 12 times 47. That is going to be subtracted by 1. That's going to be divided by the fraction. I have 2264.28. Just in case, I'm going to do that one more time. 0.05 to the power divided by 12 plus 1. This is to the power of 12 times 47. Subtract that by 1. Divide by 0.05 divided by 12. Okay, so that's 2 million divided by that. R is going to be 2 million divided by that number. Okay. 5%, again, that's not a very high number, but 5% every year. All I have to do is work really hard and save $883.28 a month. And you have a $2 million nest egg. Seems like a lot of money? Well, it could be, but think about it this way. $883.28. Okay? If I'm putting this in 12 times a year for 47 years, what does that actually turn into? That actually turns into approximately $500,000. You saved $500,000 of your own money. You worked your ass off and you've saved $500,000. But because you did it for so long, the bank is essentially giving you $1.5 million in interest. Suddenly it seems a little worth it, doesn't it? Your money, yes, it's a lot of money per month, but you are saving up $500,000. The interest is snowballing, turning into $1.5 million extra. Think about that, okay? With that said, in the beginning of the video, I asked you to try questions 1 to 5. But as you notice, the implications, the applications of annuities is huge. So if stuff like this interests you, I'd like you to continue trying as many questions as you can, getting yourself familiar with these types of questions, being able to, find unknowns here, maybe find an unknown other places, look at trickier questions, whatnot. Now get yourself ready. All right. In a couple weeks' time, a culminating will be heading your way because we're basically trying to wrap up this year with a big bang. Do your best, study hard, ask me questions, and we'll see you in the next one. Bye.